Hello everyone, this is lecture 14 of course BE544. In the previous lecture, we have dealt with vision transformers and we trained it from scratch. We have also added the function batchifying from the batchify package to batchify the image into smaller batches so we can use them with the vision transformer. And we got the performance, but the performance wasn't very high enough to generalize on the dataset in hand. So in this lecture, we are going to apply vision transformers, but with pre-trained models. As we did with CNNs, we have initiated a customized CNN architecture, and this architecture, we built it from scratch, and we trained it on the dataset, and the performance wasn't very high enough. So we moved to another step to use pre-trained CNN models using VGG 19 or 16 for example, and it increased the performance slightly. So here we will use pre-trained vision transformers and fine-tune it with the new dataset or the dataset in hand. The story simply, we have many techniques and we are trying a step-by-step to select the most promising approach that can lead to the highest performance. We have tried customized CNNs, which is less complex than using pre-trained models. Then we use the pre-trained models. We try to fine-tune the different hyperparameters. We try different techniques such as augmentation and overfitting prevention techniques. And then we used vision transformers, and in it we tried to build it from scratch so we can obtain and train that on the dataset. And here we are trying the pre-trained vision transformers. These pre-trained models can be accessed using different ways. One of these ways is using the Hugging Face community. It's an AI community and company for developing and maintaining large collection of open source libraries and tools. They provide many libraries such as the Transformers library, which provides pre-trained models and tools for a wide range of tasks, such as classification and generation. Hugging Face recently have expanded its focus to include other tasks such as computer vision tasks, including image classification and segmentation. One of these approaches is the vision transformer. As mentioned, they provide the transformers library that can be used to handle the pre-trained models, and they also include various pre-trained models which are not only related to natural language processing but also to computer vision. The pre-trained models they provide can be fine-tuned on the task and dataset in hand to improve the performance, and they also provide another library called dataset library, which allows an easy access to many image datasets that can be used to train and evaluate the models. Talking about vision transformers, Hugging Face offers a variety of pre-trained vision transformer models, including the popular Google vision transformers such as ViTs batch 16 to 24. This model specifically is pre-trained on the ImageNet, and it's a large dataset that contains over 21,000 classes. So we can use this pre-trained model and fine-tune it on the task in hand, which is called BSEH dataset. And internally, it divides this vision transformer, divides an image into fixed size batches, embeds them, and then process them using transformer encoders, allowing these encoders to capture complex patterns and relationships within the data. There are many versions of the pre-trained model supported and provided by Google. One of them, as mentioned, is ViTs batch 16 to 24, and there is another one is called VitLarge batch 32. And in the first one, they handled the image at resolution 224 by 224. That's why they mentioned in the title here 224, and they are dividing the image into 16 by 16 batches. And it's a base model, and here it's a large model, but it uses 384 by 384 resolution images that are divided into smaller patches of 32 by 32. The large difference from the base is in the fine-tuning, which means it's initially pre-trained on the ImageNet at resolution of 224 by 224, similar to the base, and then it's fine-tuned on the ImageNet at resolution 384 by 384. So it's trained, then fine-tuned, then we are going to fine-tune it again on the current dataset. To use the transformers and dataset packages provided by Hugging Face, we need to install PyTorch because this is based on PyTorch. PyTorch is an alternative to TensorFlow that can build different deep learning algorithms such as CNNs and vision transformers. So simply you can navigate to PyTorch and install it, and then install the different packages from Hugging Face. After installing the packages successfully, we need to import them. So here we imported Torch Vision, which is a library of Torch, and we imported different functions, and the same for transformers, and the same for dataset. We imported a function called load dataset, and we imported matplotlib for visualization, image from pillow library, from image reading, pandas, numpy, and scikit-learn for calculating the metrics and the confusion matrix. We have created 3 functions. One of them is the one we are familiar with, calculate all metrics updated, and we here added an epsilon value to the numerator to avoid any divisions by 0. And to understand the implementation of both of them, let's navigate to the processing of these functions. Here we defined a set of models which are pre-trained by Google. We imported multiple of them, and for each of them we have defined an output directory. So the first will be stored in the directory, the second in the second, and so on. We have defined here a set of configurations that will be passed later in the upper 2 functions, such as the testing size, number of epochs, batch size, the learning rate, and if we need to apply augmentation or not. Then we have defined the paths of the dataset and the split. Then we have looped on each combination of both. For example, the first model with the first output directory in the for loop will be trained, and it will move to the second, third, and so on. But here we have only activated the first of them and commented the other 4. We can do the same here to just train one model, but you can uncomment them to train all of the 5 models. After that, we printed the model and the output directory. Then we fine-tuned the vision transformer model using the dataset, the model name, the output directory, and the configuration set here. After that, we applied the inference phase to produce the final metrics for the testing subset. So let's navigate to each function and illustrate it. The pre-trained vision transformer function takes different arguments, including if we need apply data augmentation, testing, the test size, number of epochs, and so on. And inside this function, we have created a set of inner functions that will help us to pre-process the data. But before introducing them, let's understand the process and when we need each of these functions. First, we are loading the feature extractor from that pre-trained model, and the feature extractor here will help to normalize the data. So instead of dividing by 255 manually, here it normalizes them using the mean and standard deviation of the pre-trained model. And here we are getting the size of the feature extractor to be used later in the data augmentation. After defining the feature extractor and the normalization objects, we defined other objects for data augmentation. So if you need to apply data augmentation, we defined an object to compose a set of processes, random resizing, horizontal flipping, and then we need to apply conversion to a tensor, then normalization. If you don't need to apply data augmentation, we will just resize and center group, and we have to convert to a tensor and normalize the image. And for the validation, we applied the same 4 steps. Now we have the feature extractor, normalizer that is applied in the data augmentation. Then we have the transformation for training and validation subsets. Now we are loading the dataset using the dataset directory, and we are defining here the type of reading. It's an image folder that contains a set of classes. Then we got the training dataset and split it using the test size, or we can call it here validation size, to training and validation. Then we applied pre-processing to the training and to the validation, and these two functions are provided here: pre-process train, pre-process validation. Here simply the image is read and converted to RGB and returned in a list of a dictionary with a key of pixel values, because the model expects that the image is covered with a key of pixel values. We did the same for pre-process validation. After transforming the train dataset and the validation dataset, we got the labels and then converted the labels to IDs and made the mapping, because the model requires two versions of the IDs or the labels, ID to label and label to ID, and both of them are dictionaries. So simply in this dictionary, the keys will be the labels and the values will be the ID or index. And here is the opposite: ID will be the key and the label will be the value. After that, we created the pre-trained model using the model name, the number of labels, ID to label and the label to ID, and we defined that it should ignore if any mismatching between the sizes. Then we defined a set of training arguments such as the batch size, number of training epochs, evaluation and logging steps, the learning rate, the total number of models and the checkpoints to store locally, and if we need to report that to TensorBoard or not. And these are not only the training arguments. You can navigate to the trainer and the Hugging Face and navigate to the training arguments and check all of these arguments if you need. There are more than 100 arguments. They also provide examples and the definition and explanation for each of them. After that, we started the training process by passing the model, the training arguments, the training and validation datasets, the feature extractor, and a function to compute the metrics, and another function for the data collator. And both of these functions are defined here. Data collator will include them in a dictionary with the pixel values and labels keys, because the model expects each instance to be on that format. And the compute metrics will get the prediction and reference and compute the confusion matrix, and based on that it will calculate the corresponding metrics. And this function we implemented here as illustrated in the previous lectures to compute the different metrics. After the training, we got the results and saved the model, and then we logged the training metrics and saved them. We applied evaluation and saved the corresponding metrics locally. After that, we cleared the cache to avoid any memory issues. After the training process completes, now we have a model which is fine-tuned that we then can apply the testing split in that folder for the inference phase. In this function, it will get the classes from this folder. It will get also the feature extractor and the model, which is fine-tuned from the output directory, and it will iterate on each class and on each file, read it, and produce the output using this block. So we created a list to store the results in it for each file. We iterated over each class. We got the different files in that class. Then we iterated over the files. After that, we got the path of the image and the extension. And if the extension is not inside this list, so ignore it. And here we restricted the images to be from PNG, JPG until it reaches TIF, one of these. Based on the path, we read the image, extracted the features from the image, applied these features to the model and got the output. Then we got the logits. Based on the logits, we applied softmax and got the maximum index to get the probability of it. And to get the different probabilities, we can only apply the softmax without applying the max function. And to get the corresponding index of the class, we can apply the argmax.item. And to get the prediction class, we can access the ID to label. Now we have an ID. We can convert it to a label and get the corresponding class. Now we have the image file, the class, the predicted class ID and name, its probability and other probabilities. We can store that record and append it to the results list. It will loop over all of the classes and the files, and finally it will be stored in a CSV file. To compute the metrics, we got the actual class column and the predicted class column, applied them to the confusion matrix and plotted it. Then we calculated the metrics, and these metrics are stored in another CSV file. Now we have two CSV files, one for the results for each file and class, and another for the testing metrics, and an image of the confusion matrix. After that, we cleared again the cache to avoid any issues with the memory. After it completes, it will go to the other model and third model and so on. But as mentioned, we are only training on a single model. So when we execute the code for the first pre-trained model provided by Google, we got the following results. These are the performance metrics for the testing subset, and this is the corresponding confusion matrix. And as you see, compared to the vision transformers trained from scratch, we got high performance results, especially if we are talking about the weighted. We got a sensitivity of about 88, accuracy about 88, a specificity about 96. And because we are dealing with balanced classes, you can see that some metrics are similar in values. For example, macro specificity and weighted specificity, because the weights for the classes will be the same. As we mentioned, we defined that we need to report the results to TensorBoard, so you can use TensorBoard with PyTorch. After running the command for the TensorBoard and opening the site, we can get the different results and visualizations for each metric. So in this lecture, we have dealt with pre-trained vision transformers and know how to deal with them using the transformers package providing the Hugging Face. And we went through the different steps from getting a feature extractor, normalization, data augmentation, training process, defining trainer, defining the training arguments and the training process and validation. And then after completion of the training, we have defined an inference function that goes through the testing subset file by file and get the probability and prediction. And based on the predictions, we can obtain the final confusion matrix and the corresponding performance metrics.